Iteration is part of binary search interface that we went through. This binary search interface provides a couple of features. One, it allows you to fetch the maximum and minimum elements inside the underlying buffer, and it also provides what we call a traversal method. And this traversal mechanism that we're using makes use of the Java iterable. Since BST is an interface, we have to extend right from this interface to another interface using the extends keyword. This other interface, Java iterable, is extended in BST interface. If you recall, the iterator instance stores the iteration state. However, iterable is different than iterator. Even though both iterator and iterables are both interfaces in Java, the iterable interface needs to overwrite the iterator methods. And this kind of goes into your advanced Java. Let's take a quick look at this. This is a iterable interface in Java, and here is the iterator interface. Let's take a look at both of these. This iterable interface has a abstract method that you have to implement, which is what we call iterator. So this iterator method returns an instance of an iterator. Iterator stores data. The iterable does not store any state, meaning we don't know where exactly the iterator lands and what sort of information that underlying buffer has, which is all exposed through the iterator and not the iterable. So iterable is pretty straightforward. It implements the iterator. It's up to you how you like to expose that iterator. We'll take a look at the specific examples in a binary search tree. Aside from implementing the iterator, there's really nothing much. If you look into this iterator that's being produced has visibility into all of the underlying state of the elements because it does wrap around these elements through has next, and remove. We talked about this in list as well. So if you haven't had a chance to review these two, iterable and iterator, make sure you do that. Always remember that iterator implemented by any interface, its underlying concrete class that implements that interface is responsible for getting the iterator out. And once the iterator is out, the implementation for how you decide to wrap your underlying buffer inside the concrete class is completely up to you. Going back, the very first thing is the wrapper iterable. And the fact that we're getting this iterator out of the methods ensure that the traversal mechanism goes smoothly. And in terms of how we like to iterate these things, because the tree itself is in memory, we want to map that entire tree. So the tree looks like this, has something like this. This is a hypothetical tree. What we want to do is to map this into a data structure because you can't just apply iterations on top of this. So we have to apply iteration on top of this. This is an ADT. This could be a stack, could be a queue, could be a linked list, could be another collection, could be another list, array list, or array DQ, whichever ADT you like to map this in. How would you map an in-memory structure into ADT is the question. In this example, we're going to use in order. So in order is what we call the natural order traversal. Before we can traverse anything, before we can make use of iteration mechanism in this class or interface, we must map or taking a snapshot of the entire tree into an ADT and then traverse on it. This is the premise behind how iteration works in this example. And then we just talk about this, taking a snapshot of it, and then you can traverse through. Iterator, it's not iterable, represents the state of the tree because it has the what we call has next, and remove methods. These methodologies allows you to traverse through the tree and then trying to figure it out at any given point whether you want to do something with the value represented at each node. And that's where the binary search stuff comes around, getting the min, getting the max. In binary search tree Java class, the entire implementation encapsulating iteration, comparator, the use case for getting the minimum, getting the maximum, and also how you get the iterator and implement the has next, and remove method, they are super involved. The mechanism here also calls for doubling the size of your tree or your underlying buffer, or in this case, queue, if queue runs out of space. So this is encapsulation of all of the principles that we've talked about, from collection, from interface, from iterables, from comparable, from tree concept. The one last thing I wanted to mention about iteration is if you remove something in this underlying buffer, that's bad because as you iterate through the underlying buffer, that buffer represents the snapshot of the tree. If you remove something from that buffer, that means you're changing the tree. But you don't want to change the tree because the purpose of iterate through it is just to make sure that your source of truth does not change. By removing something off of that ADT, it's going to create inconsistent outcomes because one of them is guaranteed to be a snapshot of the tree, and then now you're changing the snapshot, integrity is changed. That is bad. So it throws an unsupported operational expression. This class, binary search, has to implement this abstract method called iterator. This is from your iterable. In this case, by default, the author of this code chooses to use in order. We will send the in order traversal mechanism type into this get iterator. So this iterator wraps around get iterator. Get iterator is a custom method. This is not Java, but what is in Java is this iterator. This came from iterable. Let's go into this wrapper methods, get iterator. This get iterator is easy to understand. For the first part, let's say this is my tree, and maybe there's another one. This is not drawn to scale, but let's say this is my tree in memory. This mechanism on the left side maps this into a queue. This is your ADT. The pre-order, in-order, post-order simply means this is my way of traversing the tree. As I traverse through each node, I want to store the node into this info queue. So this info queue is what we call the snapshot. So that now you have a hard copy of your ADT. This is a Java queue. Recall your iterator has to produce a iterator. So this iterator is right here. So you can see that the entire iterator analysis method is being produced. This iterator is a new instance that goes back to the iterator. Because the get iterator is a wrapper, it goes back to the iterator, which produces the entire iterator with a snapshot encapsulated. So this info queue is now being used to traverse. Iterator has the state informations about this underlying queue, and it's simply just going about its business. When a remove is triggered, we throw the unsupported operation exception because you don't want to make changes to that snapshot. You want to dutifully traverse through using has next and next to provide the expected outcome. So this is how traversal happens, making use of iterable. It's iterator abstract method that gets implemented. This method ensure that there is no external request would modify the state of your buffer. Basically makes it safe. And the other thing is, this is how we flatten the information into that underlying data structure, applying iterations on top of it.